Well, hello, good afternoon, everybody. I'm so delighted to see so many of you here for this tech talk, which I think really does promise to be a fascinating one. And it is all about promises, as you can see, how AI will finally, that's an important word, unlock the promise of fusion energy. So that is a big promise. Who better than to fulfill it? He is HPE Fellow AI Research Lab, Hewlett-Packard's lab. Please give a very warm HPE welcome to Paolo Faraboski.
Thank you. It's a pleasure to be here. And I'm looking forward to talk to you about hard work that we're doing in collaboration with the US Department of Energy to actually use AI to help advance the science behind fusion energy. So I'm assuming that many of you are not familiar with fusion energy. At least I wasn't. I'm a computer scientist by education, so I went through my own phase of learning what about fusion energy. So I'm going to start with an introduction of that, but also I'm going to try to focus on the reason why this is a grand challenge for science engineering. It's been around for 50 years. It's been like a promising technology for 50 years, but it hasn't moved as fast as people wanted. And I'm trying to give you a sense of why the combination of traditional fusion science together with artificial intelligence has the promise to really unlock the benefits of this technology. And then also how we can scale that so that if at some point this technology becomes available as something you can materialize in the energy grid, you can actually start collecting and making sense of all the fusion experimental data. Fusion energy, as probably many of you know, is the energy of the sun and the stars, right? So it is a process by which two atoms combine, and in fusing they release an enormous amount of energy. And this is the energy that effectively fuels the life form in our planet and perhaps in other planets, although we haven't quite figured that part out yet. And what we're trying to do in the fusion energy is effectively replicate the conditions that the sun has in its own functioning on Earth, right? So we're trying to create an experimental setting so that effectively we can fuse atoms and generate more energy than the one we put in to actually fuse the atoms. And it is a phenomenal challenge of science, and hopefully I'll give you a glimpse of why that is the case. But the benefits are amazing, right? Because it's the ultimate clean energy. We live in a world where energy is becoming a major crisis. Also, if you've seen, the increasing demands that something like AI compute is creating on the energy ecosystem is requiring us to find new forms of energy. Certainly, there's like renewable energies from wind and solar and wave energy, of which we have an example here in the field as well. But this is the ultimate clean energy because it's effectively 4 times more energy efficient than fission, but also it's a lot more clean because it doesn't really produce much waste from the point of view of the process itself. So, and again, just to give you a sense. This is sort of, if you imagine, take as a reference point, what it takes for a major city to operate in a day, that is about 1 gigawatt, which is 1,000 megawatts of electricity for a day. Today, if I do that with traditional, fossil fuel, someone in my team says burning dinosaurs, they call it, you do need 18 million pounds of coal, which is like 80 railroad cars full of coal. And to burn it, you produce 28,000, 33-foot spheres worth of greenhouse gases. So, this is basically, what the today fossil fuel generation is. In an equivalent production of energy from a fusion plant, you would need the equivalent of 3 water bottles of a combination of deuterium and tritium, which are 2 atoms that are used to be fused. And the waste product, what is interesting, it's like a few hundred balloons of helium, right? So this is just to give you a sense of if we really can get this technology to work, the outcome and the benefits for humanity are humongous, right? That's why there's a lot of energy, there's a lot of intellectual work trying to get this to actually work. And I said that, and basically, when you're creating this condition in Earth, what you're doing is you're putting together a small pod of fuel. Again, the fuel is a combination of these two atoms, deuterium and tritium. And what you're doing is you're creating enough force around it to squeeze them together so that they fuse. And in the process of fusing that, they generate neutrons, which is a source of energy that can be used to ignite some other fuel around it. And so if we succeed in doing that, then the ultimate goal of all the fusion science is to effectively create something that produces more energy than the energy you put in. And if you are familiar with some of the recent, about a year and a half ago, at the National Ignition Facility in Livermore National Labs in California, they were able to prove the first ignition, meaning that they actually measured more energy coming out of a fusion process than the energy they put in to squeeze the thing together, which was a major milestone in science, and it's kind of starting to show the path toward making this technology more real. The problem is that when we need to create the environmental conditions for this technology to happen on Earth, we actually are forced to do more than what the sun does. I mean, the sun somehow manages to create enough pressure and temperature to generate this fusion process, but within a certain footprint that has been measured, at least hypothesized by the scientists. But when we're looking at the process that you're doing on Earth, we have to create something that is equivalent of a 15 trillion pound per square inch of pressure on a really, really small fuel capsule. You imagine 15 trillion PSIs, a number that I really have a hard time imagining if you're thinking about, your car being at 30 psi, your car wheels, So, and this corresponds, because, pressure and temperature are connected together, to roughly speaking, like 1 billion Fahrenheit of temperature, so that, so the challenge is when you're creating this amount of pressure and temperature, you're generating effectively plasma, and you have to manage that process, and it is an extremely complicated scientific process. So there's like two types of fusions that are happening in the world, worldwide. One, which is the one I'm going to focus on, is laser-based, and it's called inertial confined fusion. So if you visit the facilities, and I visited the NIF facility a few months ago, but there are a few others around the world, like one in Rochester, New York, that we're partnering with. It is effectively a football field worth of lasers and amplifiers. So these lasers shoot through a series of amplification, mirrors and technologies and optical amplifiers to all converge into something that is about the size of the tip of a pin, right? So in reality, we're trying to focus 64 or more lasers with high energy to the tip of that pin, so that I'm creating this enormous amount of pressure and temperature, and I'm hoping I can ignite. So it is literally a football field, depending on the size and the energy of the facility. And all of that is going into this minuscule capsule. It is about the size of the tip of a needle, of a pin, right? So it is kind of really hard problem. And here is kind of trying to give you a sense of the type of challenges that the scientists have to deal with. So in this case, I'm showing a curve that represents the amount of laser energy that I need to shape into that pin. And imagine that the area under this curve, the integral of this curve, is the amount of energy I can spend. We're in Vegas, so let's say you got $100 to put in your various gambling machines, and you have to decide exactly at what time am I going to put how much amount of money, when and where. And so, for example, at the beginning I need to do a first shock so that I'm starting to create the pressure around the capsule. Then I'm doing, a second plateau. Then the shock converges, and I'm propagating the initial, high temperature and burst through the initial capsule gas. Then, I got a new peak. And so this is something that the scientists have found out experimentally, right? Think of this as being, and someone described it to me from the fusion science and trying to explain to me how that works. Imagine you have a water balloon that you have to squeeze at the same time from all directions, trying to get the water to compress, which is really not compressible, without squirting out in one specific area, right? So you got these 64 lasers all around this minuscule pod that need to fire at the same time with a particular shape that has been, experimentally found out. But, you imagine that the number of parameters that are involved in this particular shape are really big, right? So, I have to find, when to start the first burst, how long it needs to run. And imagine, and then keep in mind that I have a finite budget. So I cannot spend more than $100, right? Because that's the power of my lasers. Oh, by the way, I forgot to tell you that all of this happens in 3 nanoseconds, right? 3 nanoseconds, okay. So you're gonna fire all of this so that in 3 nanoseconds, you throw everything you get, and then you measure the energy that comes out, and if you are successful, you get more energy out than in. So where AI comes into play is effectively in helping understand this process and effectively generate new combinations that are better, that the scientists cannot really find by themselves because it would take them too long. And you can put in intelligent algorithms that look at historical data and try to come up with new forms and flavors of the shapes or parameters of the shape so that it has a better yield at the other end. So as you can see, this is really a grand challenge of science and engineering because it combines all sorts of technologies. And again, the scientists have been trying to come up with these techniques for the last 50 years, and now they're seeing that AI really can come to help. So in practice, the kind of process that the scientists do kind of walks through something like this. So imagine that you're starting with one experiment as a shot. You have a very limited amount of time because these facilities are shared across several teams around the world. And so, you can shoot maybe 5 times in a week. And also, some of the big facilities, after you do a really high energy shot, everything becomes radioactive, so you have got to shut it off for a week. So it's not that you can say, I'm going to do another one tomorrow, right? So you shoot the first time, then you collect the data, you do the data processing analytics. Then in parallel, what you do is you create surrogate models from an AI engine that tries to simulate what this process should be. You combine them, again, using AI machine learning technologies with the experimental data, so you're kind of up here in the right. And then this is the information that you pass on to the scientist that remains in the loop and can design the new experiment. So you got a week in the facility. You can shoot 4 or 5 times. So you got to design the new experiment. So this has got to be fast. So there's speed of doing this process. And then effectively, then you have, again, an AI-based recommender that produces a few choices of new experiments. And then the scientist is going to go in and say, hey, maybe this is the choice, because based on my experience, the choice I want to take. Then they fire a new shot, rinse and repeat. Now, the beauty of AI is that it's actually going to learn what are your preferences, and so the recommender itself, like when you're trying to watch when you watch a movie, then they know the next movie you're going to watch is trying to tell you, okay, based on what I've learned from experiments, I should be able to tell you, the next time around what is the best experiment. So we're using 2 sets of technologies. One is to create the surrogate. We're using something that's called a multi-fidelity surrogate. So we're trying to optimize the simulation time. So there's a way for AI to effectively combine different fidelities of simulators and decide when I use a fast and low accuracy and when I use, hopefully not as much time, a high fidelity simulator. And then, so that accelerates the speed of simulation, the top right part of the loop. And then we're using reinforcement learning with human feedback, which is the scientist in the loop, to effectively create an optimized control and create this recommender system that, again, recommends the best solution. So as you can see, this is a fairly complex, ideally, what the world would like to do is do the experiment completely automated. I don't think we're quite there yet. Actually, I like the fact that there's a human in the loop, because I think we're kind of still useful for something. But also the scientists have, decades of experience, and so they need to be able to kind of pick and choose what they think is the best configuration. This is basically getting rid of all the repetitive, low-level, not creative tasks and helping them to focus on the thing that really matter. So once we have helped create the experiment in the first place, then hopefully we can get to the point where we have, again, reached ignition. So we have created the conditions so that at least on a small scale, I can generate more energy than the one I put in. I mean, these lasers are megawatts of energies, and hopefully we can get something out that's more than the one we used to light it, right? So, and that's actually the second branch of fusion, which we're also working with. And this is the large-scale fusion, where there are like multinational consortia that are working to actually create a fusion power plant that ideally should be on the grid. The very aggressive objective is in like 2035. That's sort of the objective of many of these, which sounded like a long time, but right now it's like 10 years, right? And now when I say 2035, I mean the goal of putting some of these fusion plants in the grid is, I think their goal is like, they want to be able to sustain 500 megawatts for like 10 minutes. And I told them, what's the big deal? It's like, you're not going to be able to power much with that. And again, Professor Tang from Princeton told me, well, actually, think about that point in time as being the equivalent of the Wright brothers' first flight, which is basically saying, yes, we can do that. Now, from the Wright brothers' first flight to the airline industry, a couple of decades passed, but that was the turning point, right? And this is what they're aiming to achieve in about 10 years, to get to the turning point where the science is kind of stable, and then it's just a matter of engineering, as in, then you have to kind of show that you can make money and all these kind of things. And AI is going to become a really key technology also for that, because as you're moving this technology from the lab to the production, then it becomes a data problem, because all of these experiments around the world, they're producing petabytes of data. Even like one individual facility produces petabytes of data. And that data is effectively something that people need to put together as in solving a puzzle, right? That's why the scientists say we're trying to solve the fusion puzzle and reconstruct how these plants can work together. This reconstruction from data that's collected in different parts of the world by different teams is very labor intensive today. And honestly, with so much data, only a really tiny fraction of that data is ever analyzed. So the second biggest challenge of the science community is trying to solve is effectively the data puzzle. How am I going to make some sense with this enormous amount of data that's being generated during the process of putting together this large-scale fusion plant? And we're part of an initiative that is called the Fusion Data Platform, together with partners like General Atomics and others, who are basically putting together a data foundation that is based on some of the technology we have developed at Hewlett-Packard Labs, that is able to capture all the provenance and lineage and track all the data steps during the collection and analysis of these fusion power plants in a way that is timely and help, again, to remove a lot of the inefficiencies that the scientists have to deal with so that they can focus on the science. So we think that this is the second biggest contribution of AI, and this is kind of on the data side of AI, and the first one, as I mentioned, is more on the control and optimization side of AI. So to wrap things up, I'm hoping that I've convinced you that fusion is important, and while it's been like a dream for several decades, we're kind of getting close, right? I'm not saying that's a done deal, but it's definitely getting a lot closer than it was in the past. And the challenges that science and engineering have faced for the last few decades are being addressed very efficiently by AI and machine learning, not just on the control side, but also on the data side. So this is a form of a digital twinning, creating a representation of the experiments that helps me reason and optimize it. And the Fusion Data Platform is the other key element that is necessary for this technology to really move to the next step. And I hope you have also convinced you that we, as HPE and Hewlett-Packard Labs, we're kind of in the center of all of this, and we're working with the brightest mind out there. So with that, I'm going to turn it back and see if there are a few questions.
Paolo, thank you so much. Really inspirational. I can see we've got a question here. Yes, let's give Paolo a round of applause, ladies and gentlemen. I'll take your question, sir.
Thank you. Mr. Faraboshi, this is really amazing and mind-blowing to me, and I can understand why DOE will do this. But why did they choose us to do this? I mean, you're not in this business, are we?
Yeah, that's an interesting question, because normally people associate HPE with like, oh, we're providing the IT infrastructure. But it turns out that at Labs we actually have pretty deep expertise in applications of AI and development and adjustments of AI algorithm to specific problems. So in this particular case, this was the fusion energy science. So these were the actual scientists that contacted us, or decided to partner with us to submit this project proposal. And those scientists, while they could spend several years trying to ramp up their skills in AI, that's really not what they want to do. I mean, they want to pair up and partner up with expertise of AI researchers that know how to take the best of breed out there and adapt it to the things they have. So this combination of scientists and machine learning engineers and scientists, we think, is the winning recipe, not just for this, but also for several other similar type of applications.
Thank you.
You're welcome.
Lovely. We've got time for a couple more questions.
Thank you very much, Dr. Farabashi. Good question. So this work on AI and ML, all of this developmental work on that, is that being used, or is it applicable in other domains?
Oh yes, very much so. I mean, as you can imagine, I mentioned that this is a form of digital twins, right? So we're applying, and if you go and see in the floor, we're also showing that we're applying it to other areas. For example, imagine that your control problem is the data center power and cooling optimization problem, right? It's a far simpler, but still a fairly complex environment that requires simulation, surrogate models, recommenders, optimization strategies, so that you can get the best out of your data center while keeping it within sustainability targets and things like that, right? So there is a multidimensional optimization criteria, and many of the similar technologies on the AI space that we talked about here, again, simulation, surrogates, reinforcement learning for control, they're applicable in other domains. Another example, I'm not going to spend too much time, is we used it for the Carnegie Clean Energy wave energy device. This is one of the buoys that try to capture the ocean energy, and we use very similar reinforcement learning techniques. So we're seeing this as a way to push almost to the extreme, because remember those 3 nanoseconds, that's when you get up, throw everything you can, and you got no time to go back and redo it. And there are several other domains that can use derivative of this technology. So.
Thank you very much.
So, very interesting talk. I was wondering how your pipeline, AI and machine learning pipeline, should be changed or modified to tackle other scientific discipline. So you said there are some similarities, but I want to know the differences, how you improve it.
Yeah, I mean, clearly AI, it's coming from different domains, right? The application of AI in science is sort of new. And the application of AI in science comes with very significant constraints. So, I mean, the one that's obvious is that, unfortunately, science follows laws of physics, which other domains don't. So it's not that you can say, well, I'm going to ignore the second principle of thermodynamics because you can't, right? So you have to put effectively boundaries, as we call them, physics-informed AI models that actually respect some laws that are immutable, and in many other domains, if you're doing classification or language model, there aren't such hard constraints. So you have a bit more flexibility in the solutions you pick. So here, the cost of an hallucination probably could be that you're blowing the thing up completely, right? Which is hundreds of millions of dollars of a fusion plant. Now, so this is one big difference. The second big difference, and I kind of hinted at that, is the scientist in the loop, right? Is the fact that full automation in science is probably still a bit further out, although some people are postulating that. And so it is important to make sure that when you're creating your AI processes and agents, you always have a mechanism so that the scientists can go in and have the right information to pick the recommendation or make adjustments to what the AI recommends before it's closing the loop. So I would say these are two of the fundamental differences, and that's actually some of this significant value add that we're putting in as a research organization when we're partnering with scientists.
I'm afraid that is all we've got time for in this tech talk, but I think that Paolo definitely deserves another round of applause.
Yes, and just to wrap this up, I'll be around today and tomorrow, so if somebody has a question, I'm perfectly happy to continue the conversation offline. Also, there are a few other related demos that you can certainly come and visit us in the Hewlett-Packard Labs area, where you can actually speak to the experts as opposed to me.
Oh, Paolo, thank you very much.
Thanks very much. It's a pleasure.